Completed the first 3 sections in chapter 4, and my pace. Of course, I read the 3 sections as part of the work. Then my pace is, this is a July 17th video. There were 84 problems in this batch that I did, and it was 689 problems altogether that I've done so far. I've skipped a few, but in this particular group, I attended them all. Yeah. So I'm going to show the book first, as always. So the first 3 sections of chapter 4. So this is really, so in the case of linear algebra, if I go to the main table of contents, it reminds me a little bit of when I did real analysis Wade. Really, as I see it, the core of this book is vector spaces in chapter 4, eigenvalues and eigenvectors in chapter 5, and then inner product spaces in chapter 6. To me, that's really the heart of the matter. It reminds me of analysis when you do sequences, differentiation, integration. That's really like the core. And of course, in the more theoretical linear algebra books, they start here. So definitions of a vector space, these axioms get used a lot in all the problems in this section. Then of course there are examples. You run through specific cases of vector spaces, their own characteristics of the rules for adding whatever the elements are in that vector space, or multiplying by a scalar. Those two are the key things. It has to be that you can add, when you add 2 elements in that vector space, you're still in the vector space, and when you multiply by a scalar multiple, value, you still get a vector that's still in the vector space. So examples for functions and unusual vector spaces, things that are not a vector space. Of course, if one of your rules is that you multiply by the scalar and the second variable gets zeroed, that's not in the vector space. The one in the vector space should have been KU1 and KU2. And so when you try to map it, you find that it's not. So it's not a vector space. 1 times u is not equal to u. So you violate that axiom. So there's always 1 or more axioms that are violated. Then subspaces, and the key to subspaces, once again, is those 2 axioms. Can you inherit many axioms from the space that you're a subspace of, but if you prove these 2 axioms, then everything else kind of follows. So it's really the same. You add 2 vectors, you're still in the same subspace. You multiply that any one of those vectors by a scalar, you're still in the subspace. Of course, then lay out a really useful diagram. Let me see if I can zoom in and not forget to zoom back out of the vector space of continuous of all functions is the grand space. Then the subspace of that is continuous functions. Then a subspace of that is with continuous first derivative, and then all the way to continuous n derivatives, infinitely continuous derivatives like the cosine and sine, and then the vector space of polynomials. And I did remember to zoom back, so that's great. Sometimes I don't. Yep, some geometric view, linear combinations, basis vectors. Vectors that span a space eventually becomes basis vectors in the later sections. And then linear independence. Linear dependence, linear independence. Key thing here is going back. This is why I think I had this marker. Yep, that's why that marker is there. Is because, so this theorem back in 2.3 is really useful because if the determinant of your matrix, I forget what this matrix is called, is not 0, then and then also you can also show that it only has a trivial solution. Then you get independence. If it's dependent, then the determinant of your matrix is 0, and you don't just have the trivial solution. Could have said that a little better. Sorry about that. Then whether vectors are linearly dependent, they're on the same plane, or they're linearly independent, some of them are not on the same plane. Then the Wronskian, which is a really nice way to prove all kinds of problems, to show that they're linearly independent or dependent. If they're linearly independent, the Wronskian, the determinant called the Wronskian, is non-zero. If it's equal to 0, then they are dependent. So here's a good example. So you'd set up your functions and as many of them as you have, and that's a dimension, and then you do the derivatives all the way to m-1 derivative for that dimension. So of course, if it's 3, then you do 2 derivatives. You do the determinant, and then you find out whether those functions are linearly independent or not. Yeah, so that's the book. And I've already started reading the section 4.4. There was a lot of work for this. I almost made 2 videos out of this, but I figured I didn't want to make too many videos out of a single chapter. Chapter 4 is going to be the meat of it. So of course, section 1 is when you get down to the problems, you're just showing that all those axioms are true or not, depending on a specific vector space that you're given. You're given rules for addition and rules for scalar multiplication, and then you run them through. Now, in some cases, I didn't get it completely correct, because even though I said that it was not a subspace or it was not a vector space, I sometimes got the wrong axiom to fail. And that's something that I need to go back and do. But in the latter problems, for section 4.1 for the vector spaces, these were just crank them out. Yes, they're all true. The moment you look at it, you're like, yeah, of course, that's going to be a vector space. And so that worked out pretty well. Then when it came to, and I got all the true and false correct for that one. That's a rare thing, because they can be a little tricky the way the book does them. Then, of course, all this subspacing, beginning with the vector space for all functions in the negative infinity to infinity in the real numbers. Then when I got down to the problems for subspaces, as I mentioned before, there was always something that didn't work out. I screwed these one up. I went back and I read them and I realized, yeah, I see what I did wrong. I got confused. But yeah, it's all about checking really the axioms for adding and scalar multiplication. If you do those two for a subspace, you're good. I should have said it in a different way. I meant it, but it's still wrong. Somebody else who would have checked it would have not given me credits. Yeah, so this is a lot of work, and that's what I love about linear algebra. Screwed up one, but I seem to be getting better at the true and false. So here we are in the reading for section 4.3, independent and dependent sets. And so here, one thing that I really like this problem, because finally realized that you can play this game very quickly without actually doing any matrices sometimes. Just if you can add these 3 vectors in a way where you get something that's only in one of the 2 dimensions, and you can also do it for the other dimension. Okay, so I did it, I forget where it was. Oh, actually, yeah, if you can do a different combination to be a number in one dimension, and you get 2 different combinations and you equate them, then you really have a bunch of vectors all added together that equals 0. You have found a linear combination with those 3 vectors that equals 0. And of course, they're dependent. So it's all a business of getting to the point where you get all ones. Once you get all ones, that means that every one of those numbers, those components, you can call them K1, K2, K3, whatever, is 0. And there you get your linear independence. Once you do a parametrization, you're in the dependent realm. This is a very interesting problem because the way it was set up, you just do the determinant with all these lambdas, and it's all polynomials, and eventually you get the solutions, and it's either lambda is equal to minus 1/2 or lambda is equal to 1, and then I went through and I checked it to make sure that I got 0 determinant, which is what I should have gotten. Yeah, then I got into the proofs. Wronskians. Have a lot of fun with Wronskians because, of course, differentiation is very relaxing. And yeah, there was one proof, 28, where the Wronskian is the way to go. It just falls out real clean. And then the true and false. Messed one up. I don't know why I screwed this one up. I thought I was right. But in this case, another Wronskian. Was a little tricky. I cleaned it up, and sure enough, it is independent. And I screwed this one up. I gotta go back. And I've already started reading section 4.4, so that's the first 3 sections of chapter 4.